Hey everyone, welcome back. This is lesson 6-9, curving fitting with polynomial functions part 1. This is going to be a short video and then there'll be a part 2 also. The objectives for today: by the end of this lesson, you'll be able to use finite differences to determine the degree of a polynomial that will fit a given set of data. You'll also be able to use technology, your calculator, to find polynomial models for a given set of data. All right. Let's take a look at this. It says the table shows the closing value of a stock index on the first day of trading for various years. To create a mathematical model for the data, you will need to determine what type of function is most appropriate. In lesson 5-8, you learned that a set of data that has constant second differences can be modeled by a quadratic function. Finite differences can be used to identify the degree of any polynomial data. So let's see what that really means. This table tells us about the finite differences of polynomials. If your function type is a linear function, the degree of your exponent is going to be 1, so we'll just see an x. If it's quadratic, the degree is going to be x squared, 2, cubic, x to the third, quartic, x to the fourth, and quintic is going to be x to the fifth. And you will find those differences in the first row for a linear, second for the quadratic, and so on. Let's do an example of that. All right, here's an example. Use finite differences to determine the degree. All right, so first of all, let's take a look at the information that we have. And when we look at the x's, we see 2, 4, 6, 8, 10, 12, and 14. So we can see that the x value increases by a constant 2. Now what we have to do is find the differences of the y values. So what we're going to actually do is, I always just start at the end. For some reason that helps me to see it better. I'm going to say an 11.5 minus 11.4. And then I'm going to say 11.4 minus 10.5. I just kind of go backwards. For some reason that helps me. So I'm going to take a look. And so when I do 11.5 minus 11.4, you can put it in your calculator, and it's 0.1. 11.4 minus 10.5 in your calculator is 0.9. 10.5 minus 8.3, 2.2, and so on. And now be careful here. This says 4.3 minus a negative 2. So that's how we end up with this positive 6.3. So we're just looking for the differences. And notice there's nothing constant. These are all different. All right, so we don't have a constant in our first differences. So let's look at our second differences. Again, we're going to take this number now, 0.1 minus 0.9, and that gives us a negative 0.8. All right, 0.9 minus 2.2 gives us a negative 1.3. 2.2 minus 4 gives me a negative 1.8. And 4 minus 6.3 gives me a negative 2.3. So once again, there's not anything that's constant in here. We don't have anything the same. So let's try our third set of differences. Okay, so in our third set of differences, we're going to again take negative 1.8 minus negative 1.3, and I get a 0.5. Negative 1.3 minus a negative 1.8, again, 0.5. And negative 1.8 minus a negative 2.3 is a 0.5. So I can see that all three of those are constant. So I found a constant in my third set of differences. So that tells me the third differences are constant. So a cubic polynomial best describes the data. Here's another example to try. So again, let's take a look at our x's first. Negative 6, negative 3, 0, 3, 6, and 9. So we can see that the x values increase by a constant 3. So now we have to find the difference of the y values. So again, let's look at our first differences. So we would take our 151, I always go backwards, 151 minus 78 and so on. So here they are. And once I subtract everything in my calculator, I see 25, 10, 15, 37, and 73 are not constant. So I'm going to try the second differences. Again, this time I'm going to take 73 minus 37, and that's how I get 36. 37 minus 15 is how I get 22. 15 minus 10 is how I get 5, and 10 minus 25 is how you get negative 15. Again, there's not anything that's constant, so I'm going to try my third differences. So in the third differences, once again, subtracting 36 minus 22 is 14. 22 minus 5 is 17. 5 minus a negative 15 is 20. Not constant, so let's try the fourth one. 14 minus 17 is negative 3. 17 minus 20 is negative 3. So now I am constant. So that tells me the fourth differences are constant. So a quartic polynomial best describes this data. Try this one on your own. Turn the video off for a second and give it a try. Okay. When you did this one, we look at the x's first, and we see 12, 15, 18, 21, 24, and 27, and you should easily recognize that the x values increase by a constant 3. So now we have to find the differences of the y values. So you should have started out saying 43 minus 31 is 12. 31 minus 29 is 2, 29 minus 29 is 0, 29 minus 23, 6, and 23 minus 3 is 20. That is not constant, so you move on. This time, 12 minus 2 is 10. 2 minus 0, 2. 0 minus 6 is negative 6, and 6 minus 20 is negative 14. Once again, not constant. All right, the third difference is, by the time you do this, 10 minus 2 is 8. 2 minus a negative 6 is also 8. And negative 6 minus negative 14 is 8. So here we see at the third difference a constant of 8. And so the third differences are constant. So a cubic polynomial best describes this data. Okay, so believe it or not, that is the end of this very short video, 7 minutes. So hope you enjoyed it, and come back for part 2. See you later. Bye.